Hello friends, so let's talk about the potential capability CP and CPK. Many business processes are measured with variables data that have precise specifications. Recall a ABC company that manufactures parts to have a 10-inch diameter. To ensure that the parts properly meet customers' requirements, their process needs to produce part diameters that are between 9.95 and 10.05 inches. So, is the process capable of meeting these specifications? In this section, we'll use capability indices for variables data to answer this question. The capability indices in this section are ratios that compare the tolerance to the process spread. The tolerance is the width of the specification limits. The process spread is the actual variability in the process. In the last section, we determined that the process data collected at ABC meet the capability assumption. The process is stable over time, and the sample data follow a normal distribution. Because our data satisfy the assumptions, we can evaluate their capability. One way to quantify process capability is to comparing its tolerance to the spread in the process data. This ratio is called CP. Remember, the tolerance is just the difference between the upper and uh, lower specification limits. But what about the actual spread of the process? We can estimate this value. How do we do this? So this is where the normality assumption comes in. The process spread is estimated using the normal distribution. Uh, this interval shows the spread of the distribution plus or minus 3 sigmas from the mean is where almost all of the data will occur. This spread is equal to 6 sigmas. So how do we estimate sigma? This is where the in-control assumption comes in. When we collected part diameter data, we collected parts in rational subgroups. We assume that any variability in these subgroups is inherent to the process, so we can be confident that our estimate of within subgroup variation represents the true variation in the process. As a result, this variation can be used to estimate sigma, and this is a formula for CP. It is ratio of the tolerance to the estimated spread of the process. Using the estimate for sigma, we compare the spread of the tolerance with the estimated spread of the sample data. Ideally, the process spread is much smaller than the tolerance. Although there is no standard value for a good CP, many organizations strive for values greater than 1.33. This value corresponds to approximately 0.0064% out of specification. That is, out of every million parts, only 64 are out of spec. So let's calculate the potential capability for the part manufacturing process. Here, part diameters must meet specification limits of 9.95 and 10.05 inches. The standard deviation of our data is uh, 0.0113, and the potential CPK is 1.47. So is the process capable of meeting specifications? This graph itself indicates that this is a capable process. Very few, if any, part data diameters will be manufactured out of specification. When a process is capable, the tolerance is greater than the process spread. That is, CPK is greater than 1.33. So which of the following processes has a CP ratio greater than 1.33? Both processes have a CP value greater than 1.33, but only the process 1 produces parts that meet the specification. Notice that CP can provide misleading information if the process is not centered between the specification limits. This is because CP only compares tolerance with a process spread, but doesn't take into account where the process is centered. In fact, if there is only an upper or lower specification limit, CP cannot be calculated. CP simply describes the best a process could do if all instability were removed and it was centered between the upper and lower specification limits. We can use another capability metric, CPK, to factor process center into capability studies. Like CPK describes the capability of a process if all instability is removed. Unlike CPK does not assume that the process is centered between the specification limits. To understand CPK, we must first understand two other metrics, CPU and CPL. Both of these metrics indicate how the process mean or mu relates to the specification limits. First, look at the CPL. This metric is distance between the lower specification limit and the mean divided by the process spread, which for one side of the distribution is 3 sigma. CPL tells us how close the process mean to the lower specification limit. Similarly, CPU tells us how close the process mean is to the upper specification limit. CPK is equal to CPU or CPL, whichever is less, assuming we have an upper and lower specification limit. In other words, we choose a CPK that corresponds to the specification limit that is closer to being violated. Now let's look at the capability output for the part diameters. So what is CPK? Here CPL is 1.46 and CPU is 1.48. Since CPL is the smaller of these two values, CPK is 1.46. The process is capable of meeting specification now and in the future, assuming the process remains stable over time. Notice that this value is not very different from the value of CP, which is 1.47. This will always be the case if the process is centered midway between the specification limits. We've calculated CP and CPK for several datasets, but how confident can we be that these capability indices accurately describe the process? Confidence intervals provide the margin of error for capability indices. The capability output for the part diameter data includes the upper and lower limits of 95% confidence interval for CPK as well as CP. The limits for CPK mean we are 95% confident that the true CPK for the part diameter is between 1.23 and 1.7, we can use confidence intervals to conclude whether a capability target has been demonstrated. Suppose we require the part manufacturing process to have a capability of at least 1.33. Can we be confident that the process is capable of meeting specification? No, even though the value of CP is 1.46, the 95% confidence interval mm, includes value as low as 1.23. We cannot say the process has a capability of at least 1.33. So because the interval contains value less than 1.33, we cannot say with 95% confidence that CPK is at least 1.33. The true capability value may be any value in that interval, which includes 1.23. Since capability indices are rational, they have no units, so as a result, we can use them to compare the capability of different processes across an organization. For example, if the part manufacturing process has a capability index of 3.8, then it is more capable of meeting specification than the sales, packaging, or shipping process. So let's review. Potential capability indices CP and CPK tell us how good the process could be if all instability is removed. CP incorporates the tolerance and the process spread. CPK incorporates the mean of the process relative to the specification limits. As the inherent variation in a process increases, the capability indices decrease. Confidence intervals for CP and CPK provide us with a likely range of true capability values. Thank you for your listening. In the next lesson, we'll talk about the process performance, PP and PPK.